In this video, we are going to learn what we mean by a linear approximation. Sometimes we also call this a linearization of a function. So, and then also we're going to we're going to derive the formula, and then we also discuss two examples where we use linearization to solve a difficult problem. So, uh, linear linear approximation means you're going to approximate the value of a function using a line. Not that's why we call linear, but not any line. We use the tangent line. So we use the tangent line to approximate a curve near a point. So this is the idea. So let's say we have a graph. It's a graph of a function. So we're gonna pick a point. So let's say you have the point A. So that's where you want to approximate. So that means you also need to decide what point. So you can pick a point. So you can approximate the curve or the function near A at A. So what we're gonna do, we just draw the tangent line. So once you draw the tangent line, and you can see that the tangent line is very close to the function, very close to the function. For example, if you stay near around this one, and you can see there's like a very small error. So for example, here the one below is the actual value. This is actually the approximate value. The one on the top is actual value. So that's the actual value. So it's the actual value. So we normally call this is x star, the actual value, and the one in the bottom is the approximate value. So this is approximate value, approximate value. And you can see approximate value is a calculated value, and you can see the error is very small. I can even draw it here. So this error is the difference between the two. So you can see this error. So you can see error is really small. So that means if you are close to the point A, if you are close to the point A, and you can see that there's a very small error. So that's the idea. But if you when you go far away from A, for example, let's say you are like over here, then you can see the error is this much. And on the other side also, if you are over here, you can see the error is very big. So that means this linear approximation won't be accurate if you go away from A. So you have to be very careful with that. So we can write it like this. So we can say if the value of x, if the x value is close to A, if the x value is close to A, then the error is small. It's very clear from the graph too. So what we can do now is let's try to derive the formula now. And you can see that there's not much here. We just need to try to derive the equation of the tangent line. So we have a curve. Now we do the tangent line at A. So we have the tangent line. So, and then we also know that, so if you call this function y equal fx, and you can see at A, the corresponding value is fa. So what we're trying to do is we try to find the tangent line at that point. So the idea is the tangent line at AFA approximate the function y equal fx near A. All these are very important. So let's try to derive the formula. It's not that difficult, and what we know is we know that this function how do we, when you want to write the equation of tangent line, we're going to start with y minus y naught equal m x minus x naught. So that means the near the at the point x naught y naught, this is the equation of the line. So what we can do, we're going to find m and y naught. We already know x naught and y naught. So x naught equals to a in this case, and then y naught equals to fa. That's the corresponding y value. Only thing we need is the slope, and we know that the derivative gives the slope. So that means, so we start with fx. So we have y equal fx. So what we can do is we take the derivative. So once you take the derivative, so you're going to get y prime equal f prime. And then what we need to do is we can evaluate this one at A. So that means the slope is simply given by, you can say m equal, so this can give you m equal, the slope is fx naught, fa naught in this case, fa. Now what we do is we're going to plug in this under the equation. So you can see, so which is y minus y naught is the corresponding y value, which is fa, equal m as a slope, which is f prime a, and then x minus x naught is a because it's at the a value. So that's a value, a and the y value. So and then this is the equation of the tangent line. So if you move fa to the other side, you can write this one as fa plus f prime a x minus a. And then you can see this a line. What we gonna do is we can use a new notation. We're gonna say lx. So we're gonna say the new notation. Uh, so we can say, and also we can say that in this case, then you can say fx is approximated by. We write this approximate notation by this line fa plus f prime a x minus a. Now what we're going to do, we're going to use a new notation. We can use the lx. So lx, L for the linear. So lx equal, we can say fa plus f prime a x minus a. So this is what we call the linearization of the function. So it is nothing but the tangent line, just the tangent line. So we have fa and f prime a. So we call this is the linearization or the linear approximation of the function. So we call this a linear approximation of the function. So what does that mean is, so this is the equation of the tangent line. So this is Lx, that's Lx, and then we have the function already given. So that's the idea. So let's try to see how we can use this idea in two examples now. So let's look at this problem. So this is a nice linearization problem. So what it says that consider the function y equals square root x plus 5, and then part A asking find a linearization, or that we call the linear approximation, linearization of the function at x equal 4. Sometimes it calls near x equal 4, or you can say at x equal 4. Sometimes you also use a equal 4. So that's where you're gonna find the tangent line, and then use the linearization to approximate these two values. What is the square root of 10.05 and what is the square root of 8.87? And then also asking find the percentage error. So what kind of percentage error you're gonna get when you do that? Because that's kind of give you a good idea about whether this is a valid approximation. And then part C is asking is this an underestimate or overestimate? So whether you get a larger value or you get a smaller value. That's what it's asking, whether you get a small value or larger value. And the last part is asking, can we use this same approximation to find the value of square root 2? You may wonder what is the problem here? And because we always talk about that, when you use the linearization, you want to make sure that you stay close to the point x equal 4. So that may be the problem we have here. So let's try to see how we can solve this problem now. So we go one by one. So let's start with the linearization first. So we have a function y equal x plus 5 square root at you can need x equal 4. So that's the information we have. So what we can do, we can say let if x equal x plus 5 square root, and then we also need to evaluate the corresponding y value, which is f4. So we plug in 4, which is 4 plus 5 square root, which is 9. So once the square root, which is 3. So 3 is the value. So what we try to do, we try to find the equation of the tangent line. So so we have a square root function, and you can see which is shifted to the left of 5 units. So you get, so it started at -5. And if you are not comfortable with graphing like this, you can watch the video about transformation techniques. We discussed like about 10 different examples there with all different type of functions. Okay, so now let's look at the point. So the point is here is x equal 4. So we can draw the tangent line at 4. So we know the y value. Y value is 3. So we have fx equal square roots that we can write as x plus 5 to the 1/2 power, and once you take the square root, and you can see that using the chain rule, so it's 1/2 x plus 5 to the -1/2, the derivative of the inside function is 1, so we don't get that. So we can write this one as 1 over 2x plus 5 square root. So we can write it like that. Now what we're going to, we can evaluate this at the number a is 4 in this case, so you can evaluate at 4. So it is 1 over 2, 4 plus 5 square root, which is going to give you a 1 over 6. So that's the slope of the tangent line at this point. So we know the slope of the tangent line, we also know the point, so we can just write the Lx now. So or the linearization, so we can write it like this now. So we have Lx. The formula says that Lx is equals to Fa plus F prime A times x minus A. So if you plug in here, you can see if A is 3, F prime A is 1 over 6, x minus 4. Now what we need to be, you can leave it like this, that's okay. Also you can simplify if you want. So it's up to you whether you leave it like this or simplify. So let's say you simplify. If you simplify, you get 3 plus x over 6, and then when you distribute, you get negative 4 over 6, which is 2 over 3. And if you simplify, you can get that 7 third plus x over 6. You may wonder where you get the 7, and you can see the numbers we have is 3 minus 2 third. So what we can do, we're going to multiply these two numbers and subtract 2. So when you multiply, you get 9. When you subtract 2, you get 7. So that's how you get 7 over 3. Okay, so that's the linearization. So that means, so you can say thus, you can say the x plus 5 square root is approximately equal to 7 third plus x over 6. You don't leave it like that. You have to say near what point? Near, or you can say x approximately equal to 4. Only those values, so not everywhere. So that is the linearization that you were talking about. Now what we can do, we can use this linearization to approximate few values. So let's see how we can do that now. So the part B is asking, use the linearization to approximate 10.05 square root and 8.87 square root. So how you do a problem like that? So when you get a problem like that, what you want to do, the first thing that you need to do is you're going to rewrite this problem using the function, using that format of the function. Remember the function was y equal, so what's the function we had? We had y equal x plus 5 square root. That means you need to write in this form to figure out what is 5, what is x is. So we're going to say 10.05 square root is equals to, you can see that if you take 5 away, it is 5.05 plus 5. So that's how you write it. So this tells you exactly what is your x value is. So x value is 5.05, and you can see that this is close to 4. So that means your approximation it won't be bad. So and then from the formula we know that this approximately equals to 7 third plus x is 5.05, so 5.05 divided by 6. That's what the formula says. And then if you use a calculator, and you can see that, or you can just divide this. So 3.1750 up to 4 decimal places. So that is the approximate value of 10.05 used in the approximation. Now let's try to see, just for the comparison, if you use a calculator, what you actually get for this value. So if you say 10.05, so if you use a calculator, and you can see that you get approximately 3.17017. And if you look at these two values, and you can see the first 3 digits decimals are the same. You can see those digits are exactly the same. So the error starts at the 3rd place. So that means what we can do now is we can calculate the percentage error. So the percentage error is given by this formula. So what it says, the calculated value minus the exact value divided by the exact value times the 100%. The exact value is the one that we got from the calculator, and the calculated value is the one that you get from the approximation. So let's plug in those values now. So if you simplify, you are going to get 0.15%. So that means it's even less than 1%. The error is less than 1%. And you can see the x value is actually a little away from a. So a equal 4, and you can see you plug in 5. So it's like about more than 1 away from that, but still the error is less than 1%. So let's look at the next part, next one. So we have 8.87 square root. So you can write this one as 3.87 plus 5 square root, because you bring it to the right form first. Now again, as before, we use the approximation we found. So you can see this is 7/3 plus 3.87 divided by 6. And then when you simplify, you can see that you're going to get 2.97833. That's what you get. And again, as before, so if you use a calculator, and you can see you're going to get 8.87 square root, which is approximately equals to 2.97. So you can see those digits are the same, and 8, that's also the same, and then we get 2.5. So that's what you get for this one. And you may see that these two numbers are only differ at the 10,000th place. So you can see these two are like different, and then also these two. Those are the only two are different. So that means if you calculate the percentage error, this is what you get. So if you simplify, and you can see that you're going to get 0.0026%. You can see this is very small compared to the previous value. And you may wonder what happened here. And you can see in the previous one, the value that you use is x equal 5.05, and which is starting with 4. You can see it is 1.05 different from that value. For the second one, your value that you use is 3.87, and you can see if you compare to 4, the difference is only 1.13. So you can see that's like a large difference, and that is the reason why you get a really comparatively different percentage errors in these two cases. Because when you get closer and closer, and you can see, so this is the closest one, and you can see that you have a very small percentage error. Okay, so let's answer the part C now. So what is part C is asking whether this was the overestimate or underestimate. And you can see that the tangent line was above the graph. So when you look at the curve, so this was the curve, and you can see the tangent line was above. Tangent line above means you always get larger values compared to the function value. So these values are large. So that means it's always an, in this case, it is an overestimate. If the tangent line is below, it is underestimate. So in this case, since the tangent line is above the curve, you can see it is a overestimate. So the tangent line is above the curve, so it is an overestimate. So it's an overestimate. So let's look at the next part. So it's asking, can we use the same approximation to approximate square root 2? So what may be the issue here? So let's look at the problem. So we have square root 2. So if you write the format, you need to write -3 plus 5 to get 2. So that means if you look at the number line, you can see those two numbers are far away from each other. So number 4, and then we have -3 here. So you can see it's 7 point away from it. So there's like a pretty good chance that there's a large error because you're like too far away from a 4. So so that's the reason. So you can say since x equal -3 is far from a equal 4, we can use the approximation. So since x equal -3 is far from a, we normally use a for that. A equal 4, we cannot use the approximation. So we cannot use the approximation. And we can justify this by calculating the percentage error. So let's do that. Before that, let's try to find actually what we get. So if you do the same similar calculation, you can see square root 2, which is equal to -3 plus 5 square root, according to the formula, which is 7/3 plus negative 3 over 6, and if you simplify this one you will get 1.8333, and then we do the similar calculation. So if you calculate the percentage error, and you will get 29.63%, and you can see that is a huge error. This error is very large, so that means this result is actually useless. And it's also will be very clear from the graph too. If you look at the graph, and you can see this is the shape of the graph. So if you look at the tangent line, that's a tangent line, and you can see, so this is number 4 here, and if you go to this side, and like negative 3 is like almost over there, and you can see there's this error. So you can see there's a large error, and that's exactly what happened, because we try to go too far away from the 4. You have to stay around 4, but you went too far away from it, so you get a very large error. So in this kind of situation, we are not going to use that, because it's useless, because that's the error here. Okay, so yeah, that's how we solve the problem. So let's look at another problem, like which is slightly different from what we did before. So the problem says use a linear approximation to find 26 cube root. So you're going to find a cube root of a number, but which is not common. So if you need to find the cube root of 27, we know that's 3. But how you can find the cube root of 26? So this is like a really nice candidate for using the linear approximation. So there are like several ways to do it. So the easiest way is we're gonna first think of a function that can mimic this behavior. For example, we need the cube root. Since we need the cube root, first we're gonna think of, okay, we're gonna consider y equal x cube root. Or this is simply x 1/3. So that's one way. Also, you can also do like something like this. You can write this one as x plus, the closest cube root of 26 is the cube root of 27, because cube root of 27 is 3. So so that means we can write this one as x plus 27 and then take the cube root. That's like another idea. So you can pick any function that you like. Only difference is the algebra will be slightly different from every time. So let's try to use the first one and see how it's going to work, because then you can see how the math work here. So, and then if you look at the graph, this is what you get. So this is the graph you're going to get. And so this is different from the square root function, because we have the both sides for this one, positive and negative, because you can find the cube root of any number. Now we can draw the tangent line near 27. So it is 27. So cube root of 27 is 3. So that means we just try to find the equation of this line. So this is not that difficult. So let's do the work now. So you're gonna see we're gonna consider this function again. So the function we're gonna pick in this case is fx equal cube root of x. So that's the function we pick. And then this one you can write as x to the 1/3. So so the first thing we do is we can evaluate the function at 27. Why we pick 27? Because 27 is the closest cube root. Because you know that the 27 has a integer cube root, so we pick that. And then if you find the cube root of 27, so which is 3, so we know the y value now. And then we also find the derivative. So if prime x, so you can write this one as 1/3 x to the negative 2/3. And if you do the algebra, you can write this one as 3. And the negative power means you have to bring it down. So we write the square first and then take the cube root. That's what this means. Okay, you don't have to do that, but you can write it like that. Okay, now what we can do, we're gonna simplify this one. So f prime, we can evaluate it at 27, because we try to find the tangent line near 27. So it is 1 over 3. So we have 27 squared cube root. Now the question is, how are you going to simplify something like this? the easiest way is we switch the two. So what we do, we write 3 here. We can take the 27 cube root first and then square. So what we did, we switched them because you can only switch those two. And then if you simplify, now what happened is you can see 1 over 3, 27 cube root of 3 and square. So that means 3 square is 9. So you get 1 over 27. So that is the slope. Now you know the point and the slope. So we can use the point slope form now. So let's write it. So the linear approximation is Lx, which is fa plus f prime a x minus a. So we're going to plug in here. So you get 3 plus 1 over 27 x minus 27, and then what we're going to distribute and simplify, so which is 3 plus x over 27. If you multiply, you get -1 because negative 27 or 27 1, and if you simplify, you get 2 plus x over 27. So that is the linear approximation for this one. So that means you can write this one as x cube root is approximately equals to 2 plus x over 27. Make sure you always write this one. You also always need to say near x approximately equals to 27. Okay, so it's only valid near 27. If you go away from it, you don't get the right value. So now we can do the problem. So what is asking, what is the cube root of 26? So what we can do, we can write this one. We're gonna first need to figure out what value we're gonna plug in here. Since the equation has a x in there, so what you're gonna do is your x is simply going to be 26. So there are no changes like in the previous example. So it is 2 plus 26 over 27, and if you simplify this one, you're gonna get 2.9629. And as before, if you calculate the percentage error, so you can find this value from a calculator, and you will see that if you actually find the actual value, you get 2.9624. You can see it's amazingly equal to each other. So only the fourth decimal place will be different. So that means if you calculate the percentage error, and for this problem, so the percentage error, if you calculate the percentage error, you're going to get 0.016. So you can see it is even less, almost a 1/10,000th of an error. So you can see it's like it's a really good approximation in this case. You can see it's like even like 1 away from 27, but still you get a really good answer for this one. So that's how you solve these problems using linear approximations.